So anyone attempted those questions?
Yes, sir.
Very good. Question number 3.147. So we have to start from 147 itself.
Yes.
So the first question, anyone did this question?
Sir, also I had doubt from the assignment.
Yeah, fine. So we'll first finish the irodove, then we can do the assignment also.
Yes.
Fine. So 3.147. Anyone who got this answer?
Yes.
Very good. So a long cylinder with uniformly charged surface and cross-sectional radius A. So we have a long cylinder. So because this infinite cylinder, we can think in terms of lambda also. So let's say lambda is the linear charge density, which is the charge per unit length of cylinder. And the inner radius given is A. If you read the question, the lambda is not given, isn't it?
Yes.
But something else is given.
Electric field.
Yeah. So the field is given so that you can find the lambda and
Yes.
E relation. So what is the field at the surface? So field at the surface
0.
is as good as finding the field at a distance A from the axis. So for any linearly charged wire, what is the formula of electric field at a distance A?
Lambda by. Hello.
Yeah. Yes, tell me. Tell me the answer. Lambda by?
2 pi epsilon naught A.
Correct. Very good.
Yes.
So lambda, which was not given, now we know it. Now to find the current for due to the motion of this cylinder at a velocity v, you can draw any cross section which is occupying or which is covering the entire cylinder. So draw any random cross section like this. And now imagine in time dt, how much length of cylinder will cross this cross section. So in time dt, how much charge will cross this area? Can you guess? So the velocity of cylinder is given v. So in time dt, how much it will travel?
V dt.
V dt. So v dt, length of cylinder will cross it. And because the cylinder is uniformly charged, so some charge will also cross it. So amount of charge crossing this cross section in time dt will be how much? So charge is defined as lambda into
Length, which is V dt.
And what we're looking for is dq by dt,
Yes.
and that is called the current. So we call this as convection current. Why we say convection? Because here the charge itself is put on a surface and the surface is in motion. So here neither we have the field, internal field, nor we have applied the field, rather we have simply taken the charge and moving. So this is called convection current. And the answer is lambda into V, but because lambda was not given,
Yes.
so we had the relation above. So the I turns out to be 2 pi. Is this
Yes.
clear, guys?
Yes.
Everyone, is this clear?
Yes, sir.
So can you derive on your own?
Yes.
No, next. Question number 2. 3.148. So an air cylindrical capacitor with a DC voltage V applied across it is being submerged vertically into a vessel filled with water at a velocity V equals to 5 meter per second. The electrodes of the capacitor are separated by a distance d. The mean curvature radius of the electrodes is equals to r. Find the current flowing. Find the current flowing in this case along lead wires. Assume d is very small compared to r. Okay. So how to imagine this? First of all, so you have to do two concentric circle. I mean two concentric shell very close to each other. And the gap is given. And this gap is given as d. So first of all, you need to understand the diagram first. The mean radius. What is the meaning of mean radius? The inner surface will have one radius. The outer will have slightly more, because it's only d
Yes.
away, right? And d is very small compared to r. So that's why they have given the mean radius, which is the, you can say, the arithmetic mean. So the mean radius you can take as r for both the surface. The purpose of giving the mean radius is that to find the capacitance, what we need is, because this is the concentric cylinder and a potential is applied across it. How the potential is applied? The inner surface and the outer, like this. So you can say, let's say inner is positively charged and outer is negatively charged. Okay. Okay. So far so good. So we have the radius, which is, we will take the r as mean radius. Now, when the d is really small compared to the mean radius, it means you can think this is a parallel plate capacitor. And what is the capacitance of parallel plate capacitor, guys? Tell me.
Epsilon naught A by D.
Epsilon naught A by D. So when you, let's say if you're putting inside the water, so in time t, Water will occupy what level? So after empty, water will get inside. So this part is now filled with water. Because there's a rate given at which you are submerging it. So it is submerged at what rate? It's given, right?
Yes.
So if I assume this as X, let's say this is X, the way we have done in capacitance. And if I take the entire length as L, so without water is how much? L minus X.
Yes.
And this is exactly a question of a capacitor which is a part filled with dielectric and a part which is air.
Yeah, parallel.
And these are in parallel combination. Yeah.
Yes.
So what you can do is you can add the C equivalent using the parallel plate formula. So we prepared the formula as K water. So dielectric constant K absolute not. What is the area of water? So water is up to X height of cylinder. So what is the surface area of cylinder of height X and radius R? Tell me guys, what is the surface area of cylinder of height X and radius R? You can just imagine one of the surface, just take inner or outer, just think of inner surface of radius R. What is the curved surface area of cylinder formula?
Pi. So this would be 2 pi rx, right? Because height is x.
Correct. So 2 pi Rx. Excellent. We can say 2 pi Rx. The mean radius is R. So K absolute not A by D is D. Correct. Plus. Why plus? Because the remaining is
Parallel.
parallel. And that is A, so we can write as absolute not. A is how much? 2 pi R
L minus X.
by D. Correct.
Yes.
So once you know the capacitance, we have done this before also. So once you know the capacitance, you can find the charge. So charge on capacitor will be C times potential difference.
Yes.
We have given V, so I'll add V. So it is K epsilon naught 2 pi Rx by D plus epsilon naught 2 pi L minus X by D whole into V. What we can take common by the way? 2 pi epsilon naught R by D. I think this is what we can take common.
Yes.
So this turns out to be and current is defined as dq by dt.
dt. Yeah.
So just differentiate this. And once you differentiate, x becomes dx by
Dx
dt
by
and
dt.
L becomes 0. And therefore, the I turns out to be 2 pi and k minus 1. And this is given some speed v, small v.
Pi.
Yeah, we'll just put a symbol. Can you check the answer? Tell me the answer. Is this the answer?
Yes, sir. This
So
is the
anyone who got this answer?
yes.
Okay.
Okay.
Now 3.15149 I won't solve because we have done in capacitor. No, this is different. Sorry.
No, sir. I had doubted.
Yeah, this is not. This is
Yes.
temperature dependence. Okay. Now this 3.149 is to do with a lot of manipulation, or you can say approximation. So as I said, in case of temperature dependence of resistance or resistivity, the alpha is a term which is very, very small, and therefore alpha into some value is also going to be small. And because that is going to be small, you can use the approximation formula. So at the temperature 0 degrees Celsius, the electric resistance of a conductor 2 is eta times that of the conductor 1. Their temperature coefficients of resistance are equal to alpha 2 and alpha 1 respectively. Find the temperature coefficient of resistance of a circuit segment consisting of these two conductors when they are connected in series and the B part is in parallel. Okay. So first of all, draw the diagram like this. So if I choose the first resistance is R naught, the second will be, so at t equals to 0 degrees Celsius, we can assume these values. Now, at any temperature, let's call theta, this becomes R theta. So this will become how much? So we have to calculate. Okay. Or you can just call this as R theta dash. Okay. So they have different initial value, they have different alpha. So the relationship between R with temperature is R at temperature theta equals to R initial 1 plus alpha 1 into theta. Do you remember the formula?
Yes.
And similarly, R theta dash you can write as initial 1 plus alpha theta. This is how we can write. So far, so good. Is this clear so far?
Yes.
Now, what happens when you connect in parallel? So, for parallel combination, the R equal to how much? R
R.
theta. R, okay, I started with parallel. So let's start with series first. So for series combination, so let's find R series at theta or t equals to 0 degrees Celsius. So at 0 degrees Celsius, the R equal is how much? R naught
R
plus
theta
8 R
plus
naught.
N R.
No, at 0 degree. At
Yes,
0, we have to
yes.
use this. No?
Okay. Yes.
So it is R naught 1 plus 8.
And yeah,
8. Yeah, and you can call 8. Now, as you increase the temperature, we have two fresh values, R theta and R theta dash. So what will be their equivalent? So R series at, let's call RS 0, and this is RS theta. So RS theta will be how much? So R theta and R theta dash, how to write? R naught plus eta R naught. So we can rearrange. How to write? So rs theta turns out to be r not 1 plus eta. We can take common. Why we are taking common? Because this was the initial value, right? And the other term I can take common is r not theta. What we get is alpha 1 plus eta alpha 2, correct?
Yes, sir.
So what I'll do is I'll take this entire term common. Why? Because I want in the format of formula. So what I'm left with is so this is rs0, and what we are left with whole term into theta. Now we know the general formula for a general what for any combination. The temperature dependence we write as
1 plus alpha theta.
1 plus alpha equivalent into theta.
Yes.
So now you can compare. It's easy. So you have to write in the format which resemble the actual formula. Then you can say comparing the alpha equivalent turns out to be how much? So you can say the series alpha for the series will be alpha 1 plus alpha eta 2.
Yes.
Now, can you try for the parallel part in a similar fashion?
Yes.
Make sure that if something comes in the denominator, bring in the numerator, use the binomial approximation, and make sure that your final answer is something into 1 plus alpha theta. That's it. So that requires a lot of manipulation, but you can try it for some time. If you don't get it, don't worry, I'm going to give the answer. But before that, you all must attempt at least once. Okay? Do it.
Sir,
Yeah.
could you show the previous slide for us?
Okay. Sure. You have to assume things like this.
Yes, sir. Done.
Great. Then this part, you can see the other part. It won't be easy. You have to write a lot of things. Okay, so this is a good approximation based problem. And you will see that the entire chapter of called thermal physics is based on something like this only, because even there we have a similar formula. Shall I help? So what you can do is you first find the R parallel before temperature has changed. So let's say that's called RP is 0 when nothing has happened. Formula is R1 R2. So for parallel combination, we know this is the formula, right?
Yeah.
If you apply the formula, you get this, which is equivalent of N R naught upon. Now write the formula. So R P theta equals to R theta dash, R theta, like this, correct?
Yes.
And the formula is R naught 1 plus alpha 1 theta into eta R naught 1 plus alpha 2 theta whole upon R naught plus eta R naught,
Are not this.
correct?
Yes.
Now the R naught will get cancelled from one of them. So what we are getting is eta R naught into 1 plus alpha 1 theta into 1 plus alpha 2 theta upon 1 plus eta. I can take separate alpha 1 plus eta alpha 2 into theta. And I need to take 1 plus eta common. You know why? Because we have this upon this as a RP
0.
naught.
Yes.
So to get in that format, the numerator I will keep it as such. And what I can do is I can multiply all terms one by one. So 1 plus alpha 1 theta, alpha 2 theta. So this is alpha 1 plus alpha 2 theta. And then we have alpha 1, alpha 2 theta square. We'll come to that. In the denominator, we can take 1 plus eta common. Why common? Because of the reason, as I explained. And then what would be left with? Alpha 1 plus.
Yes.
Now, this formula is something which we know. And so we have three terms in the numerator. We never want any term in a format of 1 plus something in the denominator. The reason is alpha 1, alpha 2 are very small. So these very small terms are so small that we can use the binomial approximation. How to write it? And from
Yes.
binomial approximation, this will come here. Power becomes coefficient, right?
Yes.
Always remember that any term which is having two alpha multiplied together or alpha having higher degree. So alpha is very small, alpha 2 is very small. So the product is very, very small. So we can ignore. So then there's no need to write the second term. So we're left with this term. 1 minus. Okay, so again we have to do the multiplication. So let's do the multiplication. Who will do? So ignore the terms which is coming as a multiplication, just keep the single term. So that's why I said it's a lot of manipulation. So now So this will come, let's multiply 1 plus the first term. So if I multiply 1 with both, 1, sorry, the entire term with 1, the first term, so I'll get the same term, and then minus will come. And this term 1 plus will get multiplied with so there are many terms. So this will go with you can take this term and then you can take this term. Now I'll only go with the first number because second will give me a multiplication of alpha which I can ignore at very first go. So I'll write like this. So second term I'm not writing because that will be 0. And now I can take theta common. So what we'll get is alpha 1 plus alpha 2 minus alpha 1 plus eta alpha 2 1 plus eta. So just so you can see some term will cancel out. So what we're left with 1 plus alpha 2 plus eta alpha. Now you can compare with the formula. So comparing it looks almost similar, but it is not similar. You can check. The coefficient has interchanged. Earlier it was alpha 1 plus alpha eta 2. Now it is alpha 2 plus eta alpha. You can check. So it was 1 plus eta. Now it is reversed.
No plus.
It is 2 plus eta alpha. Okay. So for any beginner, this is highly intimidating. Like, don't get scared. I mean, this is very trivial calculation. And the rule is we have to every step we have to eliminate the terms which is having higher power of alpha. So when you're doing it for the first time, you can do this way, or you can expand a more multiply every possible term and then get the answer. But I think that is even more challenging. Sorry. Yes. So is this clear?
Yes.
So do practice at home. I mean, don't just leave the question okay just because I have solved. You all are supposed to solve again and again. At least try 2 or 3 times, and you will realize that okay, this kind of binomial approximation, if you use as often as this, you also become very good with the limit and continuity questions. Okay. Now 3.150 we have done in capacitor, right?
Yes.
So anyone who solved this question 3.150?
Yes, but not all I got.
So you should revise the capture
Yes.
question. So I'll not discuss this because we have done
Yes.
this. So 3.150 revise capacitor. Okay. Then 3.151. So this is like infinite series question. So have we done the infinite ladder question in capacitor?
Yes, we had done
Yes,
that,
sir.
like taking X and solving.
Yeah. So the same idea we have to
Yes,
apply
yes.
here. So what you can do is it is as good as, because it does not depend on Rx, so I can replace Rx with the similar circuit. Okay. So I can actually, or technically I can make it infinite. Okay. So you can take a 3 point. So the way of solving is very simple. You just cut a piece which is replicating itself. So R, 2R, R, 2R, dot, 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 and then we also have and this is something unknown, Rx. Okay.
Yes.
So the value of Rx will be, I mean, the answer will be free from Rx only when it is as good as infinite circuit. So the way of getting the answer is simple.
We will take that as X.
Yeah.
From the second.
So you can just repeat anywhere. So because it's a similar shape everywhere, cut it from here.
Yes.
And then you can just do a simplified circuit. So what we look for? We look for the repetition, right? And we cut it from there. So if I say the answer across A and B, if I say X is the answer, then answer across this will be also
X.
X1. So what you're supposed to do is simply write the R equivalent across A and B. So first you find the RAB using the circuit and then equate with X. So using circuit, what is the answer? 2R and X are in series.
Yes, 2R plus X, and then in parallel is R.
So into R,
Yes.
and this must be
Yeah.
X.
X.
I hope you can solve this
Yes,
quadratic.
we get is as Rx is equal to √3 minus 1R.
Right. Similar is the next problem. So again, I'm leaving that problem.
Yes.
Now 3.153. Have we done the grid problem there? Yeah.
Yes, we had did that also.
So Grid is like a you have to use this principle of superposition.
Yeah, we need to attach the wall.
So the modus operandi is, operandi is same. You have to do the similar thing what you did there. So just for the recap, if you have not observed that one carefully, so you have one more opportunity. So infinity gives you luxury of symmetry. Infinity always gives you luxury of symmetry. So every branch or every segment which you see will have resistance R. You're looking for the resistance between the equivalent resistance between A and B, which is adjacent to each other. So what we use is principle of superposition. So what exactly we do here? We make two branches, like two terminal, and you connect a battery. Let's say the potential of the battery is V, potential difference, and the current it is supplying to the circuit is I. So I will go at A and will come back from B. Because whatever goes, the same comes back. Okay. Fair enough. So if I we know, if we know, we know that this entire circuit we can replace by a single R equivalent with same battery. So what is the meaning of equivalent? If the equivalent resistance will let you withdraw a similar current from the cell as the case before. So in the actual circuit, if I was the current in the equivalent circuit, the same should be the answer. So we can say V equals to I R equivalent. So to find the R equivalent, what we use? V by I ratio. So if somehow we can find this ratio, we are done. Now this is not an easy task in this case. So what we do? We break this voltage into two parts. So a potential difference of V volt across A and B is equivalent of potential of value V by 2 here and minus V by 2 here. Both are
Yes.
equivalent. So imagine the infinity is earthed or grounded. So imagine the infinity is at a 0 volt everywhere. And imagine only one of the end, one of the node or junction, you can say. So only one junction is given a potential V by 2. So if V by 2 potential goes to one junction and there is nothing else, so in how many path it will divide?
4 parts.
And because of the infinity, can we say that all 4 paths are identical?
Yes.
If all 4 paths are identical, can we say the current will divide equally?
Yes.
So if I say this is the I current which is going from the cell, from the V by 2, can we assume each current is I by 4?
Yes.
Fair enough. If I think of the minus V by 2, because in the infinity is at 0 and minus V by 2 is less than 0. So at the junction, if I is coming here eventually, so can we assume that each branch must be contributing 1/4?
Yes.
Isn't it? So if I say this is A, this is B, do you realize that the AB branch is a very unique branch, because in AB branch, the first case gives you I by 4, but the second case also gives you I by 4 in the same direction, isn't it? So what is the principle of superposition saying? That if you combine these two conditions, you can recreate the actual condition, isn't it? And as per the principle of superposition, we add the current also. So the current in the branch will get added. So what is the net current through the branch? So through branch AB, what is the IAB? Tell me, guys. In this branch, how much current we are getting? Using the principle of superposition, I by 2. Do you realize this? I by 4 when V by 2
Yes,
is
I
giving,
by
and
4%.
I by 4 when minus V by 2 is giving, because we have to combine the two situations together. So the net current will also add up or superimpose, and the answer becomes I by 2. Okay. Now, what is the formula for the potential difference using Ohm's law? So VAB, can we say VAB equals to I by 2 into R?
Yes.
But VAB itself is V, no? So V by I turns out to be how much? And that is the definition of R equivalent, V by I. So the answer is how much? R by.
R by
So in general, if you remember, if I have explained that also, it is 2R by number of branches. So 2R by number of branches. What is the number of branches leaving a junction?
4.
So 2R by 4 is the answer. Okay, you can
Yes.
apply for anything. You
There
can
it
apply for,
was NC by 2.
yeah, it was NC by 2.
Yes.
So if you remember the answer, C equivalent is NC by 2. Replace C by 1 by R. Once you replace, you will get the answer. So to convert the formula, you have to substitute the formula this way. Okay. So we had the discussion. Just a recap so that you can understand better. Although this is not required, don't worry about this. 3.155, we have done already in class.
Yes, so 5, 4, and 5 both.
Yeah. So 5, 4 is done, 5, 5 is done. 5, 6, no.
No, but I got.
Okay. So you got the answer for this.
Yes.
So this was using the RC circuit, right?
I derived it.
So the space, let me draw the question. Three point 156.
6.
The space between two conducting concentric spheres. Okay. The space between two concentric conducting concentric spheres of radii A and B is filled with homogeneous poorly conducting medium. Oh. Okay, so far so good. The capacitance of a system is C. So C is given. So what is the formula for C if you remember?
1 minus A. Yes, 1 by
Find the resistivity of the medium if the potential difference between the sphere when they are disconnected from the external voltage decreases eta fold during the time interval delta t. So let's say the resistivity of medium is rho. Okay. So when we have a potential source, let's say potential source is having voltage V. You can connect it the way you want. So what is the charge? What is the, okay, we know the capacitance and we know the potential difference. So charge will be how much, guys?
C
CV.
into V.
So let's call this as charge Q naught. Okay.
Yes.
Now, what is the resistance of this circuit? R will be how much? Anyone? You can find the similar fraction.
4 pi B minus A upon AB.
4 pi rho, no? How to find the resistance of a spherical medium? So we are at dr equals to rho dl by A.
Upon. Yes. Huh.
So rho by 4 pi, no?
That only answer.
So A to B. So the
From A
answer
to
is
B, huh?
rho by 4 pi 1 by A minus 1 by B.
But
Am I
yes.
correct?
Huh.
So what is RC value?
Achha, okay, you asked us.
So RC will be a rho epsilon. That's formula.
Yes.
Okay. Now now this is the part which I haven't taught. So the charge as a function of time t is q naught 1 minus, sorry, q naught e power minus t by tau. And v in general is, you can say, or you can say something v initial, v naught, confusing for guys. Okay. So potential across the capacitor at any time t, you can attest q naught by c. So what they are saying is that this value is decreasing by eta times the initial value. So q naught by c is the initial value. To make it simple, what I'll do is
Sir, but can we not take it like V will be proportional to minus eta, so like that?
E will be proportional to,
Or minus eta because it is decreasing n-fold times.
we have to take the log and all.
I did that only. I took log.
So the voltage, okay, this is the potential at any time t. This I haven't taught, that's why I'm like hesitating, because I will teach after some time. So anyway, as for the question, this is the initial potential of the capacitor upon eta after time, basically delta t by tau. This gets cancelled. So e to the power minus delta t by tau is 1 by eta, which is like, this implies e power delta t by tau is eta. You can take log both sides, ln eta. So the tau becomes delta t by ln eta, and tau itself is rho epsilon naught. So the rho will be, don't worry, this I will teach you shortly after, maybe after today's lecture. So the answer should be delta T by epsilon naught ln eta.
Sir, I did something different. Can I send you?
Yeah, yeah. I
And I
see.
got the answer. Yes.
Yes, that's really interesting, which I would like to see in fact.
Yes.
So, okay. Why you wrote V proportional to
I
N?
miss because I thought like after reading the last line that when it is disconnected from external voltage,
Mhm.
uh, decreases n-fold times during the time interval delta t.
But that is not suggesting that it is going to be proportional, right?
Okay. Okay.
But anyway, I mean,
Okay.
if you have got the answer, it is
Yes.
something. I mean, although strange, but interesting to know. So I'll keep this answer. I'll research about it. Why a wrong method is giving right answer. So it's a good thing. Anyway. So we'll come to this very soon. So this part we can leave. Next we can go to. So there are some simple way of doing this also. So a current will establish across the plate because the charge will discharge in a way, and you can write the KVL sign kind of thing. So next part is 3.157. We have done 3.157.
No, I think, but it's easy.
Yeah, we have done.
Yes, we have done.
We have done. Two metal balls of same radius in a
Yes.
homogeneous pool. We have done this question. In fact, this question we
Yes.
did in the class. Okay, so 3.157 we have done. Okay, next is 3.158 is called the electro.
So
Or
we
you
have
can
done that also.
But
this is called electrical image. We should not do this question.
A part I wasn't getting that.
No, I'm saying this you can question you can leave. 3.158 is okay to leave because
Okay.
So we
the
did it in the last class.
3.158. No, we did
No,
in
no, we didn't.
no we did only 157. 8 is a question based on the electrical image, which is not difficult, but just because it's not part of our syllabus, we can just ignore it. So if you remember the electrostatic, I have discussed the electrical image. So when you have a anyway, if you have a metallic sheet, infinite sheet, then and there is a some sphere of radius a, and it is at a distance L from the sheet, right? And it is given that L is much bigger than a, so you can treat as a point charge, isn't it? So for every point charge, the metal will act as a mirror. So you can think metallic mirror, and it will create a complementary charge on the other side. You can think this way. And a hypothetical charge will appear here. You can imagine a reflection. But the charge you have to assume is minus. So basically, everything is on the upper side because we have nothing physical below it, right? So the below is empty space, but you can imagine a mirror. Assuming the reflection, you can find the resistance. So how we find the resistance, guys? So we write the resistance R equivalent to V by I. There are many ways. So you can find V. Yeah, V by I you can find. Or if you remember the other way, current equals to how we used to write? Current density equals to I equals to J dot dA, and we can always use this formula as sigma E dot A. So it is 1 by rho flux. So the R equivalent we write as voltage upon I, and voltage you can write as V, and I we can write as phi E by rho. We have the formula R equivalent is rho potential difference by electric flux through each sphere. You can just run through each sphere. You can write as potential difference by flux. This is the like formula, which you can manipulate this way. So the answer will be rho. Potential difference is kq by A minus of minus kq by A, if you remember. And flux is q by epsilon. We know this formula for flux due to any charge q. So the flux will start from here and will terminate here, but we can take as coming here. So the R equivalent will be rho, and it will become twice q 2q by A into q by epsilon naught. Q gets cancelled. So 2 rho by rho by A into epsilon naught into K we can write as 1 by 4 pi. This also gets cancelled. So what we are getting is rho by 2 pi A. Now this is the answer which we got earlier, but now the reality is the distance the charge will travel is from the positive charge till the plate itself. The other half is entirely not opposing, right? The other half is actually, like I say, physically not creating any resistance, isn't it? Do you realize this? So can we say the resistance of the first half is R, the second half is also R, technically? So we are looking for R only. No? So what we got is 2R, not the R. So what is R? Since 2R is what we got. So the reality is R equal by 2, which will the answer be. If you look at the answer, you will get this answer. You can check. It is half of the answer which we got earlier. So 3.157, if you know the answer, if you divide by 2, you get this answer. Okay. Can you check?
Yes, it's there.
So what they're asking? Oh, sorry. So this is a B answer, the answer for B. For A part, I have done in electrostatics, hopefully. If not, then leave it. Not required. Come to the next part. 3.159. Okay, it says again similar problem. So all are of one kind. So let me do this one. 3.159. So this is also called the telegraph wire. So two long parallel wires. So let's say, so instead of wire, we have to draw a cylinder because the radius is given to us. So it is just like you need to manipulate this calculation. It's a trivial calculation, but you have to do it. So one is, let's say, positively charged because the voltage between them is given V, and space between them is filled with some poor connecting medium. You can think this way. So this is the resistivity rho, and the radius given is A. So you can think as a positively charged rod, which is uniformly charged. So imagine the electric field lines that infinite cylinder creates. If you remember, it's a cylindrical shell kind of. So the field lines will be readily outward, right? So you can,
Yes.
if you remember the Gaussian surface thing and all. So if I choose a cylindrical surface, okay, let me choose a cylindrical surface just near the, this is, so if I choose a cylinder surface very close to the cylinder, and why I'm doing this, because I want to use the local form of Ohm's law. Of any length. So what is the surface area of the cylinder? So because it is very close to surface, we can say the radius of my surface is same as the radius of the cylinder, right? Can we say the radius of my
Yes.
cylinder is same as that of the wire? So what is the flux to the wire? Or you can say what is the current density or whatever. You can write the way you want. So the best way is I equals to flux upon rho. This is what we derive, right? You can see. This is the best way to approach. So what is the current through this L length? Because we are doing it for particular length. So question, let me read the question first. First we'll find the resistance per unit length. So let's find the resistance of only this part. So what is the current of this part, guys? Flux. And how to add flux? Tell me. Charge within the center. How much
Q
charge
by
you want?
epsilon.
Yeah. So what is the charge? What is Q? So you can add in terms of lambda, no?
Yes, lambda into L.
Lambda into L. Yeah. Upon epsilon.
Yes.
All right. So this is the current, and the current remains same as we know. So the resistance of this part will be how much? R of length L will be how much? V by I.
V by I. Yes.
So V is given, and I can attach lambda L. Rho epsilon naught. All right. No, there is a problem. Oh, this L is different than the L. Okay, this L is given. It's called L dash. But people confused. Now, how to get rid of lambda? Because lambda is actually not a given. Any idea? So for that, we have to use, see, in case of infinite cylinder, what we know that we cannot find the potential. We can find potential difference. That is the problem. Okay. So what we need to do is we have to choose a point P at a distance x from the center. The same point will be how much far from the other axis?
L minus X.
And we know the electric field formula. So electric field at point P, the net due to both will be lambda by 2 pi epsilon naught x, the first one.
Yes.
And second one will also pull it on the right. So
Yes.
plus. So net will be like this. So delta V, we know the formula minus E dot dx. So the state is EP dx minus, and lambda by 2 pi epsilon naught, you can take common. What we get is 1 by x, 1 by L minus x. And the limit will be where to where? That's a big question. So that's very interesting. What you need to know. We take the limit from surface till the next surface, because inside there is no field, right?
A to L.
X equals to A to L minus A. You go to surface,
Okay, surface to.
because inside there is no field, no?
Yes.
So we think this way. And delta V is given to us. It's V actually. I'll just take the magnitude. So ignoring the minus sign, and the first integration will be dx x will give you ln x,
Ln X
ln L minus x with
minus.
minus sign, it become minus sign. So V turns out to be lambda by 2 pi epsilon naught. This is a better way of getting the answer. So ln x upon L minus x, A to L minus A, how much it is coming? Upper limit. Ln L minus A by A minus lower limit, which is same as it will become 2 times, right? Both will add up, right? Because it's the inverse of each other, no? You can just invert it and we can add it. So how much we are going to get? The answer. And L is much bigger than A, so we can attach lambda by pi epsilon. Why pi? Because this 2 will cancel out with this 2 summation. ln L by A minus 1. Okay. Now L is much bigger than A, so L by A will be much more bigger than 1.
Yes.
And if you separate one, you can approximate by
ln.
that's approximate answer. This is called potential difference formula. No, that's too difficult for you guys. Yeah. You can leave this. So potential difference we got is how much? Lambda by pi epsilon naught ln L by A. We need resistance per unit length. So we need to find the current, which is okay. So we can write as current equals to sigma. No, why we got to below the answer? Just I think some mistake I made below. Flux is P into some mistake I made. Okay, I'll just check it. I'll just do it again. Leave this part. So we got the V value. And current we can write as current density into area, which is 2 pi AL. Right? 2 pi A is called some value H. So potential difference is constant. I is J and the J is sigma into E. But E, okay, that's the same thing. It's a flux only. V into 2 pi H is flux. It's a flux by resistivity. It's the same thing. Anyway. Okay, I think they must have been answering that. So I need to check the answer first. So okay, we'll go with the same thing. So I equals to flux by rho. So R equivalent is how much? V by I. Lambda by epsilon naught. Okay, V is given. Why I'm writing here. So V is given V and I we can write as flux by rho. And flux is lambda, whatever height you take, H by epsilon naught. And lambda we can replace by lambda by epsilon naught. This implies temporal. Lambda equals to epsilon by H. Okay, weird answer. So the wire 2.159. Let me check the answer. Something that makes me make a mistake. It's rho by pi ln. H should come in the numerator. I'm written in denominator. Potential difference, we got the answer correctly. The H should have been in numerator. That's why upon H will cancel out. But I am getting in the denominator. It's strange. Something I misunderstood. Let me check.
Sir,
Yeah.
on the next page,
Yeah.
I think you epsilon naught by lambda we have to put. So,
The H should get cancelled. I
oh
mean,
no, no.
H should get cancelled. So in calculation of potential difference, I chose field formula, which is correct. So that's fine. So that part is okay. The and current is defined as okay, E into 2 pi RH flux open loop. This one. Yeah, I think I remember this answer was incorrect. H will come here. H will come. I mean, H will not go away. Yeah, I think this is the right answer. They have made some mistake in the answer. So they have cancelled the H, but we are getting H in the denominator, and it is not going to get cancelled. Correct. So what they have mentioned is this answer. This. So they have cancelled H. How they have cancelled? It's, resistance of a medium current length. If I take L length, then the flux coming out will be okay. Is into 2 power H. Okay. But H will come in the denominator. All right, you can keep the answer like this. Yeah. This is fine. So for H length of the wire, the resistance will be this much. There is no mistake in this question. So as far as I remember, I think the answer was wrong in one of the questions. I should have rectified the answer. Okay. The A part is easy. A part is like this. So you can see the two wires from this direction. So let's say look from this side. The cross-sectional view, because that's easy to do. So what you'll see is only two circles. And you have to choose a point which is equidistant from both. So point which is equidistant from both is this point. This is R, this is R. So this is only we can draw the equidistance point. This is given as L. So the electric field, if this is plus charge, if this is minus charge, the field here will be like this. We know from electrostatics. The plus will get field like this, and minus will get field like this.
It will be towards right.
So the resultant is going to be like this. So if I choose this angle as theta, this is going to be theta because the field is this E and E, and this theta will become this theta, this theta. So anyway, so if I call point P, EP is how much, guys? 2E cos theta. So the net field is 2E cos theta, and we know the field formula due to what do we say? Line charge, infinite line charge. Okay. So that is lambda by 2 pi epsilon r. We have done this before.
Yes.
And cos theta we can write in terms of L by 2 by r. Am I right? Can you guys see this? Clear? L by 2 r, cos theta is L by 2 r.
Yes.
Come on. So 2 gets cancelled, and the answer is lambda L by 2 pi epsilon naught r square. And current density is sigma into E.
Sigma into.
It's local form because we want local current density, we can use this formula. So 1 by rho TP is lambda L by 2 pi epsilon naught r square. And lambda we can replace by this formula because we have this relation, which you have to use anyway. L by rho 2 pi epsilon naught r square into, and what is the value of lambda? Epsilon naught pi v by ln L by A. That's a big answer. Something gets cancelled. So the J turns out to how much? L V upon rho R square. I think 2 is also coming. Ln L by. I think this was the answer. Can you check again? Let me see. Is this the answer? Yeah, LV by 2 rho R square ln L by A. Correct. So you can see a lot of the usage of local form of Ohm's law. Okay. The next is 3.159. The rest is RC circuit duties. Let me solve the question number 3.163. What is the homework?
Which question?
3.163.
Yes, still there.
In the last class.
We did 16 class.
163 we did. Huh?
Yes, yes.
Yes, sir.
So, what else I gave? This much.
You gave 60 and 61 also.
60.
160, 160.
That 16. That you can leave because anyway you learned this very soon. It's
Okay.
called RC circuit.
Okay.
We have done a lot of this today. Okay, so we can go to the next concept. Let's learn some concept. So the basic series parallel grouping question I am skipping. The reason is I am discussing capacitor. So what you are supposed to do is do all this problem using the idea of capacitance. Just formula will switch. So the series of resistance will add and parallel will have inverse addition, right? If you remember. In capacitor, it is vice versa. Here in capacitor, the parallel capacitors gets added, and series you add the inverse values. Inverse of equivalent is sum of inverse for series in capacitor, parallel in resistor. So we'll see the idea of solving circuit here. We can start the current. So we'll directly go to the rules actually. Current divider rule. If you recall the capacitor sector, we had a charge divider rule. Do you remember?
Yes.
So on a similar line, we have something called current divider rule. So what we do here? Are you guys also getting the noise? So we have a okay divider will be applied for the parallel circuit. If you remember, am I audible, guys?
Yes.
Yeah.
Are you getting the noise from outside?
No, sir. We could just hear your voice.
Great. So this mic is working fine. Now I'm getting too much noise. Okay. So if a current I is coming and it faces the junction, and we have two parallel paths, each with resistance R1 and R2, then current will divide I. No? I. So what remains same here? For each resistor, because they are in parallel, so what will be same for both? For parallel resistor, what remains same, guys? Tell me. If two branches are in parallel, then what will be same for both? Am I audible? Am I audible, guys? Hello, hello, hello. 1%.
Yes, sir.
If two branches are in parallel, tell me, what is the property of parallel branches, parallel circuits? They have same terminal, right? If branches are in parallel, they have same terminal. And if they have same terminal, what else
Hello.
will be same? Yeah, tell me.
So the voltage will be same.
Voltage remains the same. Yeah.
I was asking for a long time, now you're asking. The voltage of parallel branches remains. That is a simple takeaway. So whenever you see two branches which are in parallel, then you must say that their potential difference or voltage will be same. So current will distribute in a fashion to V, the voltage. So if I say this end as A and this end as B, no matter what path you choose to go from A to B, whether the upper or the lower path, because every point in a circuit will have a unique potential. So potential is a property of a point, not of the circuit. Every point will have one potential value. And since A is same for both the resistance, B is same for both the resistance, so you can say the potential of each terminal is same. So the difference is going to be same for both. And from Ohm's law, the potential difference of A minus B, you can write as I1 R1 from the upper branch, but if you write from below, you will write
I2
I2 R.
I2.
So we know that the ratio of current distribution will follow the inverse ratio of resistance in parallel. And that is logical. Current will prefer to go from the branch which offers lesser resistance. So if we have two branches with high and one with low resistance, so a large chunk of current will go through the low resistance and a small chunk, a small part will go through the high resistance. So if I make a path which is perfectly conducting without any resistance, then theoretically all current will go through the zero resistance path in parallel. Remember, in parallel, and nothing will go from the path with finite resistance. So if you have two parallel connection in which we have zero resistance path and a resistive path, it is natural for the current to choose the path which offers nothing in terms of resistance. And that condition is called short circuiting. So whenever that happens, when 2 points of a circuit, you can say accidentally gets connected with a wire, then those 2 points become short circuited, which means they will have same potential and all current will go through that path. That's very interesting. That you may be wondering that, sir, you're saying that there is no potential difference. It's a pure path. And you're also saying that there is, all current will go through that path. So potential difference formula, if you look carefully, it is IR, the Ohm's law. And V is the potential difference. So if R tends to 0, the V equals to IR, which also tends to 0. It means it is not the current which is making the potential same, it is the zero resistance which is making the potential same. So no matter what is the current, if R tending to 0, the IR will also tend to 0. And the potential difference will be so negligible that it's good to say they're almost equal. So we'll come to that short circuiting in a while, but what we need to know that the current will divide in the inverse ratio of resistance. Now, why you need to remember this? Of course, you can solve and get the answer, but when you solve numericals and circuit problems, knowing this idea will make the calculation really fast, and not just fast, it will make it almost mentally solvable question. So we'll see how you can solve question mentally with this side. So you know the resistance, the ratio, and from the Kirchhoff's current law, if you remember the KCL, which is like a conservation of charge, can apply for conservation of current. So the incoming current at the junction A is how much, guys? What is the incoming current at the junction A? It is I. What is the outgoing current from junction?
I1 plus I2.
So the sum must be equal to I, isn't it?
Yeah.
If you know the sum of two numbers and if you know the ratio of the number, can you find the number? That's pretty easy. Can you
Yeah.
solve and tell me what is I1? So what is I1, guys? Tell me. Solve and tell me. Solve and tell. Don't see it. Solve and tell. Everyone.
Hello.
Yeah.
I2 will be IR1 upon R1 plus R.
Correct. So what is similarly what will be I1?
IR2 upon R1 plus R.
Okay, so 1 will be 2 upon 2 plus 1.
Yes.
Into total. And 2 will be 1 upon 1 plus 2. Is this part clear, guys? Tell me. Yes or no?
Yes.
Now, do you need to derive it or you can write it directly?
Directly.
You should actually. Let's take one simple number. Tell me, guys, what is I1?
40 by 3.
What is I1?
Okay, I told I2 is 40 by 3. So
What is I1?
8 by 3.
8 by 3. So it's 2 by 12
Yes.
into 16. Correct?
Yes.
What is I2? In subtract, you can get the answer.
40 by 3.
But you should not do this calculation over. I want you guys to know the direct way of doing it. So I1 will have the 2 upon 12 to 16 and I2 will be 10 upon 12 to 16. This is clear? Everyone tell me. Whenever you see a parallel branch, you find the current and then divide as per the current divider rule. Okay, guys? Clear?
Yes.
Yes.
So the next is, imagine you are solving a circuit. Can you find the current through each branch? Yeah, I want current here. Here. What is I1, right? So first of all, don't solve. You simply, can you reduce the circuit?
Yes.
So what is the R equivalent?
4.
R equivalent is 4, correct. Very good. So R equivalent is 4. What will be the current to the battery? The cell?
3.
So 3 ampere will come like this. Now 3 will come at the junction. Now it will get 2 paths to divide.
Yes.
So upper will get how much?
1.
1 ampere, because it's 5 by 15, which is 1/3.
Yes.
Yeah.
This is 2 ampere.
2.
And again 1, 2 will meet again, become 3 ampere.
3.
All done. So knowing the divider rule is effective to solve question fast. That's it. No need to do all calculation again and again. If something is very much trivial, better you should know it. every trivial calculation we can kind of eliminate, and we can become effectively faster in solving circuit. Mostly mentally we can do the calculation. Now the other question would have been, what is the potential across 10 ohm resistance? I know the current, I can tell the potential difference using Ohm's law. So what is the potential across 10 ohm?
10.
It is 10. So what is the potential across 5 ohm?
10 only.
Well, it is parallel.
Yes.
So what is the potential across the 2/3 ohm resistor?
2.
It's 2. Because 10 is there.
Yes.
Out of 12, 10 is gone, 2 is left. So that's the answer. Everything is well defined and well satisfied. So now the thumb rule is, the moment you come across a reducible circuit in which the R can be reduced into single value, first you reduce it, find the net current through the set, walk the path, as and when required, divide the current, get your answer. That is kind of effective way of solving question. Reduce your effort. So let's see a very nice JEE advanced problem, which can be solved almost mentally. Yeah, I said almost. Just
Hello.
Okay. So this is 2, 4, 2, 8. 2, 2, 8. 2. Find the current through 4 ohm. I want just this current. What is this? Can you solve it without using pen?
Sir, if we start reducing from right, it is coming like the same.
Correct, correct. It is like a reducible circuit,
Reducible.
and all are parallel and
Yes.
having same value. So first you shrink everything. What is the net value of resistance across the terminal of the cell? Our terminal is here, right? A and B. So tell me what is the equivalent resistance across A and B, guys? Everyone. It is reducible from which side?
Is it 4?
Yeah, it is 4.
Yes.
It is 8, na? I think 8. No, 4. Yeah.
Check.
8, 4. 4.
Like the
4,
4 is a bit
4. It is 8 actually. 8. Yeah, it is 8. So I can make the value 16 volt. Now it is fine.
Yes.
So the 2, 4, 2 is 8. This is 8.
Yes.
This 8 is in parallel with this 8. So this we can
Yes.
reduce to 4.
4,
Okay.
Again
That 4 and that 2 will become 8 and 8 and again 4. This 4
Again
and this
4.
it 8, na?
Totally. Yes.
So the current through this will be how much? 16 by 8, which is 2 ampere.
Yes. Yes.
Now that 2 ampere will reach at this junction. It will get 2 paths below. But we know that the entire value is again 8 only. So all are in parallel. This is also 8. From here to here is 8 and this is also 8.
Yes.
So 8 and 8 are in parallel. So current will exactly divide into half.
Half. 1 and
ampere, 1 ampere. Coming to here, again 2 branches, equal value.
yes.
1 by 2 and 1 by 2.
1 by 2.
So I is
Oh.
1 by 2 ampere. That's the
Yes.
answer. Understood?
Yes.
So you can see that J advanced question we can solve mentally. No need to solve each step. If you know the current divider rule, it's pretty easy. Okay.
Yes.
Any doubt in this, guys? Tell me.
No.
Anyone? Archit? Garv? Manav?
No, sir.
Okay. So you can solve a large number of reducible circuit the way you know. So we'll go to something concept called voltage divider rule. Voltage divider rule. So what is voltage divider rule? So we are just taking two resistors in series, and now V is the voltage. So of course, the voltage that will appear across each resistor will be less than V, correct?
Yes.
So the first resistor will get a V1, and the second will get V2, right? V1, V2. Now what is remains same? The current remains
Same.
same, correct? So we can add V1 equals to, I can write IR1 numerically, Ohm's law, and V2 equals to IR2. Now we are not trying to calculate I. If we are assuming I, then we can write like this, yes or no.
Yes.
And what we know is that the ratio we can find from here. So V1 by V2 will be how much? R1 by R2.
Yes.
What else we know? The sum of voltage is equals to, the sum of voltage is equals to, okay.
Yes.
So it's the same thing. If you know the ratio, if you know the sum, can you
Yes,
find
here
each
it
value?
will be directly like V1 will be V
R1.
R1.
Correct. So it is directly proportional.
Yes.
So again, this is something that you should remember. If you try to solve all these things, then it will take a lot of time and potentially it becomes slow process to solve the question of circuit. In circuit, many things we should do mentally. Okay, most of things, if not all. So that's very simple. That if you give me two resistors, I'm not saying 3, 4. If you give me two resistors, then the division I can do it without solving. Correct? So let's
Yes.
apply this for some questions. So the example one. If you have 2 ohm, 6 ohm, and if I say 10 volt, what voltage will appear across 2 ohm?
Pi by 2.
If I call V1 and V2. So V1 is 2 by 8 into 10.
Into 10.
So it is how much?
Pi by 2.
2 for 5 by 2. And V2 is how much?
15 by 2.
15 by 2. So if you add both, you'll get the 10, right?
Yes.
Is this clear, guys?
Yes.
Manav, are you getting?
Yes, sir.
Okay. Archit,
Yes, sir.
Garv.
Yes, sir.
So this two divider rule, you should always be pro with this. No matter which circuit you are facing, if you know these two things, you can reduce your effort drastically. So let me give you this question. Let's see how fast you can solve.
That is 3.
Yeah, 3 ohm,
Okay.
6 ohm, 4 ohm. So technically, the left one we can reduce, and therefore we can eventually convert this into two resistors, right?
Yes.
Now my question is, what is the potential? Or let's say my question is, what is the let's find. What is the potential across 4 ohm? So 6 and 3 are in parallel. Can we reduce it? So if you can reduce it, what you can do? The left will become 6 and 3. How much? 6 3
2.
is 2. So this is as simple as this circuit. So potential across 4 will be how much? Tell me. Tell me.
Will it be 4?
Potential across V2. For two resistors in series, what is the potential across a given resistor? That resistance upon sum of the resistance into total voltage.
Yes. Okay, you asked 2.
You said
Yeah, so
1.
1 is 2.
So definitely V1 will be 4 volt. So V1 V2 we can find easily. Okay, just like I mean this is basic practice. If you do then while solving a tough question, at some stage we can apply the voltage divider, current divider, then we can get rid of some rigorous calculation. Okay. So we'll see a quick recap of the KCL in the context of R circuit. KCL for R circuit. So what we know for any junction, the summation of all incoming current
Is equal to
summation of all outgoing current. Okay. So if we have a junction, and you know the potential of the endpoint somehow by some means, you know the potential. So what we are supposed to find? So this is the part of some big circuit which is not shown to you. And we are looking for potential of the junction. So what is given to you? First of all, you need to realize what is known to you. You know the potential, not the voltage. You know the potential of each end. The other end. We have one common end, which is the junction, and the other end. So you know the potential of each end. V1, V2, V3. What you're looking for? Potential of the common end, the junction, which is not known to you. How to solve this question? Given the potential, how to solve? So we have to choose some current distribution. Now the question is how to choose the current distribution? The answer is the way you want. There is no restriction of the selection. So what I'll say is that all of you choose some random distribution the way you want. Everyone. Don't write what I'm saying or what I'm going to write. You just choose your own. Okay? Everyone. Choose your distribution, write the law, and then I'll come to that. Okay. So you all have taken the distribution as per your own choice.
Yes.
Now write this equation. Your own choice selection, incoming, write incoming equals to outgoing.
Yes.
Everyone written? All done?
Yes.
Tell me guys, everyone.
Yes, sir.
So if all of you have written the current distribution and if you have written incoming equals to outgoing, always remember current flows from high potential to low potential. So let me take my own value. So I am taking something like this. I1. Okay, I'll take which I always prefer. All outgoing. All out. So for me, nothing is incoming. So what I can write? Outgoing equals to nothing, because the way I have chosen is this way. If you have taken something else, stick to it. Don't change it. Okay. Now we have to think of Ohm's law. Now really comes the Ohm's law. We are writing Ohm's law. So Ohm's law says potential difference upon resistance I equals to V by R, right? So I1, the way I have taken, is going towards left. So which potential is high, V or V1?
V. V
So
minus
I will
V1.
write V minus V1 by R. 1. Similarly, I will write I2 equals to V minus V2 by R2 because I have taken in that way only. If you have taken other way, write accordingly. Which means if you have taken I1 towards it, then V1 is bigger and V is smaller. So you have to write the value, a positive value. High minus low upon resistance. 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 Is this clear to all of you?
Yes, sir.
Yes, sir.
Now you have to find V. So rearrange. Take it right or left. Take all V term together. So I can write V 1 by R1, 1 by R2, 1 by R3. And then I can take V1 by R1, V2 by R2. So V turns out to be how much? Now, if you see, if everyone, whoever the way you have taken, your end result is going to be same. This one.
Yes.
So have you? I mean, taken the different distribution and getting the same answer? Yes or no? Or are you guys getting different answer?
Same answer.
Same answer. Anyone whose answer is mismatching? See, guys, if you are not writing, again you are making the same mistake. All of you must write. To learn, you have to write. Done, everyone?
Yes, sir.
So your answers are matching, and the answer is matching with this answer.
Yes, sir.
Very good. Now the question is, when we use the Kirchhoff's current law, KCL. So we use anywhere, but there is some like a rule to use it. So I will take the similar example as we have done in capacitor, to get some momentum, and then we can solve the inverse symmetry problem.
Sir,
Yes.
sir, here the Wheatstone bridge concept will remain
Yeah.
same, right?
You will learn Wheatstone bridge. Yeah, it is same, but you will learn in separate. We have topic called electrical instrument. So
Okay,
we are going to learn in detail everything. Okay. So voltmeter, ammeter, meter bridge, Wheatstone bridge, potentiometer, and post office box. These all devices we are going to learn separately. So we have three phases of in this chapter. So we have first the normal circuit problem. Then we'll go for something called RC circuit, which we left in the capacitor. So we'll see how to solve those circuits in which the capacitor and resistor come together. Okay. Then how to attempt it. And then we'll learn the some energy analysis of such circuit. So it's a separate topic and rigorous topic called energy analysis in RC circuit. And then we'll go for the something called electrical instrument, and that is the end of your this chapter, current and electricity. Okay, so let's me just give you a idea how to solve. Let's say this is 12 volt. So we have a circuit, as you can see, 2 ohm, 4 ohm, 8 ohm, 2 ohm, 4 ohm, 8 ohm. We have a battery, 12 volt. That's it. Okay. Now we know that to apply the KCL, what are the some thumb rule?
We need
We
to
remove
get
the
the
battery.
junction.
We remove the
Yes.
battery and we replace with potential. So we choose one as 0, another as 12.
12.
So we are going to choose 2 ohm, 12 volt, 4 ohm. But this is 0, this is also 0, this is also 0, because nothing is in between. Okay, this is 0. And this I can draw like this, 8 ohm. Done. So simple.
Yes.
Yes,
And
sir.
now let's say if you want to find this voltage here. So this is V. And because we know the end value, can you find the V value? Junction rule. What is the formula? End value 12 by 2, 0 by 8, 0 by 4.
0 bar.
It is clear?
Yes.
Upon inverse of all resistor, 1 by 2, 1 by 4, 1 by 8. Nothing we're done. This is 6 upon. LCM is 8. So 2 4 is 8, 4 2 is 8 and 1. So it
48.
is so 48 by 7 volt. So if we this is the 48 by 7, it's we are done. Okay. So now if you want to find the current through this 4 ohm, let's say if you want to find the current through 8 ohm, all questions can be solved just like this. So now this is once you get the voltage, you can go back to actual circuit and let's say current will go like this, I1, I2, and this way, I. So what is
Ohms,
I1? It's easy to find I1, Ohm's law.
Yes.
V by 4, correct?
Yes. 48 by 20.
48 by 7 by 4. So this is how much? 12 by 7
12 by 7.
ampere. I2 is how much? It's half, 6 by 7. Just check. Correct?
Yes.
And because I know I1, I2, so there is no need to find I, because I will be Kirchhoff's current law. So the answer is just add it, 18 by. See, all done.
Yeah.
This is just another way of attempting the same problem. You could have done by the current divider rule. We could have reduced it. Now the problem is if the calculations are really bad, if you really in the process of a reduction, you get very bad fraction. It will piss you off in the examination. You will leave it. Only if it is mentally doable, if you can reduce it mentally and you can get nice value, it is suggested to use that method called the reduce the circuit and get the answer. But if you are looking at the question and you realize that, okay, if I go through that method, my fraction is going to become really bad, leave it. The moment you realize my fraction is bad, think about KCL. Okay. So will it come naturally? No, it will come only through practice. So I'll give you a lot of questions for practice, don't worry. So you will have sufficient practice problem of KCL. Okay. And if you want to recap, you can recap the capacitor chapter, you will come to know that how to use that. Okay, it's clear.
Yes.
Okay, so I'll solve one question called inverse symmetry question in the next lecture. I think you guys are tired. You need some time to digest all this idea. So better, I would say, revise quickly from notes, capacitor, try to recall, and start solving the current and electricity from AC order. So you have seen the irodove. Irodove question. See, every question that we are solving in class, just practice those questions. No need to solve extra question from irodove. Okay.
Okay.
So what you need to solve extra is the assignment. Okay. Now, those who are finding all those things again difficult, I will suggest you only start with SC Verma and you finish it. So not everyone is supposed to solve everything. It's not required. You take something which you can complete, because what really matters is completion. If you choose a small part of it and if you are able to complete, you will get better confidence to attempt in the examination. If you attempt something which you are not able to complete, you will get stuck in between, which I don't suggest. So if you can solve all questions, I'll say you do assignment. If you can solve less question, because you need more time, start with SC Verma and just finish completely end to end. Right
So
now,
we have a circuit assignment also then.
yeah, I'll give you separate assignment for circuit. Yeah, so that will have more circuit problems. Okay, and probably if you have solved irodove and those assignment, you are not supposed to solve Verma. That's not required.
Okay.
So in fact, if you see those questions, you can do it mentally. So develop these ideas, and after all this, you can do the, if you are done with everything, do the JEE problem, because that is relevant. Okay. So for beginner, I will suggest, if you take more time, you start S-Verma and finish it. Okay. If you can solve more questions, maybe 200, 300 questions, then do from assignment. And anyway, I'll give you question from S-Verma anyway, because there's some part of S-Verma which is really good, which I want you guys to solve. So, okay, I'll keep on guiding what to do, what not to do. But right now, what I want is that start solving. Simply start solving. The first assignment which I gave, I'll request everyone to solve all questions. Why? Because those kind of questions are not relevant in Verma. So Verma ji having different category of questions. Those questions are not there. So it's good to attempt, finish it, and you will get next assignment very soon. Bye guys, take care. Good night.
Thank you so much.
Bye.
Nice.